Good morning, dear students. Today we will discuss about the H parameter or hybrid parameter of the transistors in the subject of analog electronics. So, what is the H parameter model in transistors and what is the use of these H parameters in transistors? So, the equivalent circuit of transistor can be drawn using simple approximation by returning its essential features. So these equivalent circuit will aid in analyzing transistor circuits easily and rapidly. Two-port device and network parameters. A transistor can be treated as a two-port network. The terminal behavior of any two-port network can be specified by the terminal voltage V1 and V2 at port 1 and 2 respectively, and current I1 and I2 entering parts of 1 and 2 respectively as shown in this figure. That is the two-port network in which there are two ports. One is port 1 at the input and second one is the port 2 at the output. Of these four variables V1, V2, I1 and I2, two can be selected as independent variables and the remaining two can be expressed in terms of these independent variables. This leads to various two parts parameters out of which the following three are more important. So first one, Z parameters or impedance parameters. Next, Y parameters or admittance parameters. And next one is H parameters or hybrid parameters. So why is the name hybrid parameters? The four parameters associated with this model are input impedance, current gain, and output conductance. Since their units are completely different from each other, this set of parameter is called as a hybrid parameters. So if the input current I1 and output voltage V2 are takes as independent variables, the input voltage V1 and output current I2 can be written as V1 equal to H1 H11 I1 plus H12 V2 and I2 equal to H21 I1 plus H22 V2. The four hybrid parameters here H11, H12, H21 and H22 are defined as follow, that is the hybrid parameters. So what is the H11? H11 equal to V1 upon I1 with V2 equal to 0. So this is the input impedance with output port short circuit. Next parameter H22, that is equal to I2 upon V2 with I1 equal to 0. That is the output admittance with input port open circuit. And next hybrid parameter H12 equal to V1 upon V2 with I1 equal to 0. And this is also as a reverse voltage transfer ratio with input port open circuit. And next one is hybrid parameter H21, that is equal to I2 upon I1 with V2 equal to 0. That is the forward current gain with output part short circuit. So these are the four parameters. of hybrid parameters. Next one, what is the dimension of H parameters? So the dimension of H11 is O, and the dimension of H22 is Mo, and H12 is dimensionless, and also H21 is dimensionless. So as the dimension are not alike, they are hybrid in natures, and these parameters are called as hybrid parameters. I equal to 1 equal to input, and not equal to 2 equal to output, f equal to 2 forward transfer function, and r equal to 1 reverse transfer function. So notations used in transistor circuits: HIE equal to H11E equal to short circuit input impedance, H0E equal to H22E is the open circuit output admittance, HRE equal to H12E equal to open circuit reverse voltage transfer function, and HFE equal to H21E equal to short circuit forward current gain. So these are the notations used in transistor circuits. So the hybrid model for the two-port network that is shown in this diagram. Here V1 equal to H11 I1 plus H12 V2, and I2 equal to H1 I1 plus H22 V2, and also V1 equal to H1 I1 plus HR V2, and I2 equal to HF I1 plus H0 V2. So these are the values of voltage and currents of this two-port networks, that is the hybrid model. Next, transistor hybrid model. Consider the simple CE configuration or common emitter configuration of figure. For this configuration, the four variables are as follow. One, input current I equal to IV. Second, input voltage VI equal to VBE, base to emitter voltage. Third one, output current I naught equal to IC, that is the collector current. And fourth one is output voltage V naught, that is the VCE, voltage collector to emitter. So here given a common emitter transistor circuits. First circuit is the the common emitter transistor circuit, and second the equivalent circuit of this common emitter transistor circuit. In this circuit, by applying KCL at the collector node, Kirchhoff current law, so expression for H parameters or CE configuration can be obtained from above equation by let VC or IV equal to 0, and H parameter for CE configuration are, if we consider VC equal to 0 or HI equal to VE upon IV, where HFE equal to IC upon IV. So HFE is the current gain. Now, if we consider IV equal to 0, then HRE BVE upon VCE. that is the voltage gain, and H naught E equal to IC upon VE. So this is the admittance, output admittance. Hence, we can neglect HRE and H naught E while drawing the H parameters equivalent circuit. Such an equivalent circuit is called as the approximate hybrid equivalent circuit, which is shown in four uh, above figures. Note that dependent voltage source BCE has been replaced by a short circuit, and H naught E has been replaced by an open circuit. Next, H parameters or hybrid parameters model for a common collector CC configurations. So H parameter for CE configuration are, if we consider VEC equal to 0, where VEC is the voltage across the emitter to collector, and HIE equal to VVE upon IV, and HFE equal to IE upon IV. Now, if we consider IV equal to 0, so HRE equal to VVE upon VEC into H naught E or equal to ICE upon VEC. If these parameters are specified for a particular configuration, then suffix E, B or C are also included. For example, HFE, HIE, HIB are H parameters of common emitter and common collector amplifiers. So using two equations, the generalized model of the amplifier can be drawn in as shown in this figure. So there are various forms of the uh, different configuration, common emitter, common base, and common collectors, and different parameters, just like input impedance and gains, current gains, voltage gains, and output impedance. So HI input impedance for the common base will be BB upon IB, and for common common emitter will be BB upon IB, and for common base this will be BE upon IB, and for common collector this will be BB upon IB. And next one is HR, that is the voltage gain. So for common emitter this will be BB upon BC, and common base VE upon BC, and common collector this will be equal to VB upon B. And next for current gain HF, for common emitter IC upon IB, and for common base IC upon IE, and for common collector IE upon IB. And also next one is the H naught. So this is the power in watts. So for common emitter this will be ICBC, and for common base this will be ICBC, and for common collector this will be equal to IEVE. So merits of hybrid models. There are some merits for the hybrid models. First one, H parameters can be easily measured, and they can be calculated from the static characteristics of transistor. Manufacturers provide H parameter in their data sheets, and H parameters can be used easily and conveniently in circuit analysis and design. And there are also some demerits of the H parameters. So the hybrid parameters suffer from a major disadvantage that they are defined only for a particular set of operating conditions. And next one is the parameters of other equivalent circuit can be determined for any region of operation within the active region and are not limited by the single set of parameters provided by the specification sheets. Next is the small signal amplifier analysis. So in small signal amplifier analysis, we represent the transistor amplifier circuit in the form of two-port network, and this two-port network represents the transistor in any one of its three configurations, or common emitter, common base, and common collector. So these are the three configurations of the transistors. And what is the meaning of analysis? So in the process of analysis, we obtain the expression for the following parameters of an amplifier. First, current gain; second, input resistance; third, voltage gain; fourth, output resistance. And by comparing the values of these parameters with the other, we can judge the performance of the amplifier. So there are some steps to follow for analysis of a transistor amplifier circuit. So first, we replace the DC voltage source by a short circuit. And second, replace each of the coupling capacitor and bypass capacitors by a short circuit. And finally, replace the transistor by its hybrid equivalent model, or RE model, and proceed with the analysis. So now we will discuss about the field effect transistors. So what is the field effect transistor, and what is the advantage of field effect transistor as compared to BJT, bipolar junction transistor? So the field effect transistor, FET, is a transistor that use an electric field to control the shape and hence the conductivity of a channel of one type of charge carriers in a semiconductor material. FET are unipolar transistor as they involve single carrier type operations. So the concept of the FET, the BJT, though it was not physically implemented until after BJT due to the limitation of semiconductor materials and the relative easy to manufacturing BJT compared to FET at the time. So FET can be majority charge carriers devices in which the current is carried predominantly by majority carriers or minority charge carriers devices in which the current is mainly due to a flow of minority carriers. The device consists of an active channel through which charge carriers, electrons or holes, flow from the source to the drain, Source and drain terminals conductors are connected to the semiconductor through ohmic contact. So source and drains are terminals of the FET, and the conductivity of channel is a function of the potential applied across the gate and source terminal. So there is total three terminals in FET. One is source, second is drain, and third one is the gate. So FET is the three terminal semiconductor device. So drain, though, which is carriers leave the channels. Conven- Conventionally, current entering the channel at D is designated by ID, drain to source voltage is VDS, and source through which the carrier enter the channel. Conventionally, current entering the channel at S is designed by the IS. And gate, next terminal is gate, the terminal that modulates the channel conductivity by applying voltage to gate. One can control ID. So here are the symbols of BJT and FET. So in BJT, there is the total three terminals, base, emitter, and collector. And the BJT is generally two types. One is the NPN and second is PNP. And field effect transistor also two types. First one is N-channel FET and second one is P-channel FET. So first figure show the N-channel FET symbols, and second figure show the P-channel FET symbols, in which three terminals, gate, drain, and source. All FET have source, drain, and gate terminals that correspond roughly to the emitter, collector, and the base of BJT. Most FET have a fourth terminal called the body, base, bulk, or substrate. This fourth terminal serves to bias the transistor into operation, and it is rare to make non-trivial use of the body terminal in circuit designs, but its presence is important when setting up the physical layout of an integrated circuit. The size of the gate length in the diagram is the distance between source and drain. The width is the extension of the transistor in the direction perpendicular to the cross section in the diagram. Typically, the width is much larger than the length of the gate. A gate length of 1 micrometer limits the upper frequency to about 5 gigahertz and zero point 0.2 micrometer to about 30 gigahertz. Next is the classification of the FET. So there are two types of FET. One is N-channel FET and P-channel FET. And also FET also divide in third type, that is the MOSFET and metal oxide semiconductor field effect transistors. So MOSFET again divide in two parts, two types. First one is enhancement MOSFET or E MOSFET. Second one is the depletion MOSFET or D MOSFET. And also E MOSFET divide in two parts. First one in N channel E MOSFET and second P channel E MOSFET. And also depletion MOSFET have two types. One is N channel D MOSFET and second P channel D MOSFET. So that is the classification of the field effect transistors. These are the systematic symbols for JFET. First symbol is for the N channel JFET and second symbol is the for P channel JFET or junction field effect transistor, in which three terminals gate, source and drain. These are also some symbols of N channel JFET, N channel JFET offset gate symbols and P channel JFET. So these are also some symbols of the different JFET junction field effect transistors. Next one is the operation of a JFET. So this circuit diagram shows the operation of the JFET. Here the one voltage source applied between the gate and source and second between the drain to source DC supply voltage across these terminals. So from operation of this circuit diagram, when neither any bias is applied to the gate or when VGS equal to 0, nor any voltage to the drain with respect to source. For example, when VDS equal to 0, the depletion region around the PN junction are of equal thickness and symmetrical. Second, when positive voltage is applied to the drain terminal D with respect to source terminal S without connecting gate terminal G to supply as given in this circuit diagram, the electrons which are the majority carriers flow from terminal source to terminal drain, whereas conventional drain current ID flow through the channel from drain to source. Due to flow of this current, there is uniform voltage drop across the channel resistance as we move from terminal D to terminal S. This voltage drop reverse bias the diode. The gate is more negative in this case with respect to those points in the channel which are near to drain than to source. Hence, depletion layers penetrate more deeply into the channel at points lying closer to drain than to source. Thus, base-shaped depletion region are formed, and when BDS is applied, the size of the depletion layer determines the width of the channel and hence the magnitude of the current ID flow through the channel. Next one is the MOSFET device. MOSFET stands for metal oxide semiconductor field effect transistors. And MOSFET is transistor used for amplifying or switching electronic signals. Although MOSFET is four-terminal device with source, gate, drain, and body B terminals. So in MOSFET there is four-terminal device. The body or substrate of the MOSFET often is connected to source terminal, making it a three-terminal device like other field effect transistors. Because these two terminals are normally connected to each other or source circuit internally, only three terminals appear in electrical diagrams. The MOSFET is by far the most common transistor in both digital and analog circuit, though the bipolar junction transistor was at one time much more common. So in these figures, P-channel FET circuit symbols, these are the same as the circuit symbol for N-channels device, except for the direction of the arrow heads. So first symbol is J for the JFET, second symbol for depletion MOSFET, and third one is the enhancement MOSFET or E-MOSFET. So in MOSFET, there is total four terminal: gate, drain, source, and base. So what is the advantage of FET over conventional transistors or BJT? So FET is unipolar device. It means operation depend on only one type of charge carriers, that may be holes or electrons, and FET voltage control device, because here gate voltage controls drain current. So this is the voltage control device and unipolar device. And FET have very high input impedance, approximate 10 to the power 9 to 10 to the power 12 ohm. So that is the very high input impedance. And in FET, source and drain are interchangeable in most. So we can interchange the source and drain, and FET used as a low frequency application. So these are the some advantage of FET as compared to BJT. And also FET low voltage, low current operation is possible, or we can say that FET is low power consumption device. And also FET less noisy as compared to BJT, because in FET there is one junction, but in BJT there are two junctions. So in FET less noisy as compared to BJT. In FET no minority carrier storage, turn off is faster. So this is fasting device as compared to BJT, set limiting device, and FET is very small inside, occupies very small space in IC. So low voltage, low current operation is possible in the MOSFET device. And also zero temperature drift of output is possible in the FET. So there are some advantage of FET as compared to BJT. What we have some disadvantage also of FET. So there are some disadvantage. First, it has a relatively low gain bandwidth product compared to a BJT. The MOSFET has a drawback of being very susceptible to overload voltage, thus requiring special handling during installation. So this is the disadvantage of the FET. Next, the fragile insulating layers of the MOSFET between the gate and channel makes it electrostatic damage during handling. This is not usually a problem after the device has been installed in a properly designed circuit. So these are the some disadvantages of the FET applications. The most commonly used FET is the MOSFET or metal oxide semiconductor field effect transistor. The CMOS complementary metal oxide semiconductor process technology is the basis for modern digital integrated circuit. This process technology used as a arrangement where the usually enhancement mode or P-channel MOSFET and N-channel MOSFET are connected in series such that when one is on, the other is off. In FET, electrons can flow in either direction through the channel when operates in the linear modes. The naming convention of drain terminal and source terminal is somewhat arbitrary, as the devices are typically but not always weld symmetrically from source to drain. This makes FET suitable for switching analog signal between paths, multiplexing. With these concepts, one can construct a solid state mixing board. For examples, a common use of the FET is a amplifier. For example, due to its large input resistance and low output resistance, it is effective as a buffer in common drain or source follower configurations. There are some reference books for this topics. First one is the electronic device by Millman and Algas, and second one is the principle of electronics by Baxi and Dorsey. There are some multi-choice questions for these topics, and we will discuss these multiple choice questions now. So first question, a JFET or a junction field effect transistor is similar in operation to option A diode, option B pentode, option C triode, option D tetrode. So here correct answer is option B pentode. A JFET is similar to operation to pentode bulb. Next questions. The transconductance of FET depend upon option A drain supply, option B the type of FET, option C gate to source voltage, option D gate current. So here the correct answer is option C, gate to source voltage. So transconductance of FET depend upon the gate to source voltage. In next questions, the voltage gain of cascade amplifier using FET is option A, product of two voltage gains, option B, equal to CD amplifier, option C, almost equal to CS amplifier, option D, none of the above. So for the voltage gain of cascade amplifier using FET is a product of two voltage gains. So here correct answer is option A. Next questions. A FET is a control device, whereas bipolar transistor is a control device. So option A, current voltage, option B, drain gate, option C, gate drain, option D, voltage current. So here correct option is the D, because FET, field effect transistor, is a voltage control device, whereas a bipolar junction transistor BJT is a current control device. So option D is correct answer. And next, in FET, the drain voltage above which there is no increase in the drain current is called voltage, a critical voltage, a pinch off voltage, option C, breakdown voltage, option D, peak of voltage. So here correct option is B, pinch off voltage. In a FET, the drain voltage above which there is no increase in the drain current is called a pinch off voltage. So correct answer is option B. And next questions. FET acts as a constant current source in option A, ohmic regions, option B, breakdown region, option C, pinch off region, option D, both B and C. So here correct answer is A, FET act as constant current source in ohmic regions or resistance regions. The next questions, the gate input current of a FET is of the order of option A, amperes, option B, microamperes, option C, milliamperes, option D, hundreds of nanoamperes. So gate input current of an FET in order of the hundred of nano amperes. So this is the very minor current. So here correct answer is option D. Which of the following is the common features between FET and bipolar junction transistor BJT? So what is the common feature between BJT and FET? So option A, difficult to bias, option B, low voltage gain, option C, low input impedance, option D, current control device. So correct option or correct answer is D, current control devices. Common features between FET and bipolars. In next questions, in the resistance region or ohmic region, the FET can be used as option A, voltage variable capacitor, option B, voltage variable inductor, option C, voltage variable resistor, option D, none of the above. So here correct option is voltage variable resistor, because in ohmic region field effect transistor can be used as a voltage variable resistors, VVR. Thank you.